So our very first speaker, she is an expert in video streaming, video coding, and computer vision. And that's just naming a few. And she is very productive as a researcher. She has published hundreds, literally hundreds of journal and conference papers. Professor Ya Wang works at the New York University at the Tandon School of Engineering. She has one foot in the Department of Electrical and Computer Engineering, and the other foot is firmly placed in the Department of Biomedical Engineering. And on top of that, in addition to being Associate Dean for Faculty Affairs, she's also the lead of the New York University Video Lab. So it's safe to say that she has her hands full and more than enough to fill her days. And we are grateful that she has accepted this invitation to share both her time and her insights with us. And it might be a bit chaotic to give her a true and warm, immersive applause, but there are ways of getting around her. So there's this wonderful function here on Zoom that can give you a virtual, give her a virtual applause. And with that said, we will welcome Professor Ya Wang to give her talk on 360-degree video streaming. Please give her a warm applause.
Oh, I'm sorry, I was able to unmute myself. I didn't realize that. Thank you very much, Ragnhild, for that wonderful introduction. And I'd also like to thank all the conference organizers for inviting me for this wonderful opportunity to present our work. So let me start the presentation. I'm going to start sharing the screen. So as Ragnhild just mentioned, we will be talking about our work in 360-degree video streaming. In case some of you have not had the experience to stream a 360 video, let me show you an example. This is a screen capture when I toured the magnificent Notre Dame before it caught fire last year on YouTube. Because I don't have a head-mount display, I was just using a plain computer with a mouse to orient myself. As you can see by dragging the mouse, I can view different directions of the interior of the Notre Dame. This gave me an immersive experience as if I was standing inside the cathedral and being able to look around easily. Of course, if you have actual head-mount display, you will see a more seamless experience. Just as with 2D video, there are many ways you can consume 360 video, be it video on demand, live streaming, or interactive streaming. They differ in terms of the delay tolerance that's acceptable, and also the way you interact between the server and client. And unlike with 2D video, where you have to watch where the cameraman wants you to see, with 360 video, you can focus on wherever you want. So this is will provide the participant a immersive experience. Today, popular video streaming platforms already support on-demand and live 360 video, and 360 video conferencing products are also on the market. However, today's solution still lacking in the quality of experience that they can provide. So here is an outline of my talk. I will start out by discussing the resolution and the bandwidth requirement. Then I will discuss the general idea of FOV adaptive streaming and their challenges. And next, I will describe our work in different types of video applications, including video on demand, live streaming, and interactive streaming. I will also discuss our work in FOV prediction using deep learning. So let me start out by discussing the resolution and bitrate requirement of 360. The example I just showed you actually, as you can see, the 360 video can be represented in the so-called ERP format, or equirectangular projection, in which the spherical surface will be projected onto a 2D rectangle. So the resolution of 360 video is often described in terms of the resolution of this 2D rectangle. The example I showed you earlier, in fact, is only a 4K by 2K video. So it's actually below this entry level represented here. Ultimately, we would like to have a resolution that matches the resolution of our retina, which is approximately 64 pixels per degree. With that, that will translate into a 24,000 by 12,000 2D video. And if we want to have a 3D experience, we will need a stereo pair that will double the resolution, double the bitrate. So even with significant compression promised by the next generation video coding standard, we will still be looking at over 3 gigabits per second. And if you have an interactive applications, then this will further double. To be able to stream such video smoothly over the network, we will need even higher bandwidth. Obviously, this will present a significant challenge even with the ever-increasing capacity of the network. So how should we stream 360 video? The example or the resolution requirement I showed earlier assumes that we send the entire 360 view span. But as we can see on the right, a viewer at any time only watch a small portion of the 360 scope. Therefore, sending the entire 360 scope would be a waste of bandwidth. As shown on the right, in fact, we may only watch 1/8 of the entire scope. And in other words, if you have a limited bandwidth and you want to describe the entire area, you would have a low quality. A natural solution would be to send only the actual FOV. However, this means you cannot deliver until the user feedbacks her own FOV. This, unfortunately, requires the round-trip delay to be below 20 milliseconds, which is not feasible when the participants are separated across far away, for example, in different continents. An alternative solution is to predict the future FOV and send only the predicted FOV. So this sounds very good. However, we have to be able to handle the situation if the predicted FOV is wrong or partially wrong. In that case, you may see a black area in the pixels, which is outside the predicted FOV. Of course, you can also just repeat what you have received in the past. In that case, instead of black, you will see a frozen area. In order to maximize the prediction accuracy, we would like to minimize the prediction horizon. However, in the streaming applications, the prediction horizon equals to end-to-end delay between the sender and the receiver. In order to reduce the delay, we can use short buffers. However, when you use a short buffer, video frames may not arrive in time, causing video freezing. So a significant challenge in FOV adaptive streaming is that we have to design the system to be robust to both FOV prediction errors and network bandwidth variations, while maximizing the rendering quality. And there were multiple unique problems for 360 video, including FOV prediction, FOV adaptive coding, and read allocation in different regions. I will discuss our solutions to some of this problem in the following slides. And notice different designs are necessary for applications with different latency requirements. Before I move on to different applications, I'd like to first describe ways to enable FOV adaptation. By using tile-based coding. As shown here, the spherical surface is represented as a rectangular frame in ERP. With tile coding, we divide the entire rectangle into many small tiles, and the tiles would appear like this on the sphere. And we will code each tile separately using 2D video coding tools. And this way, depending on the predicted FOV, we can control the rate or quality of each tile and send only those tiles that's within the predicted FOV. Notice that other coding methods are possible. For example, viewport-based coding, as illustrated here, where we will code the entire area together. And this could be more efficient in terms of video coding, but is less flexible as tile-based coding. So therefore, the systems that I described in the following would all be tile-based. So let's first look at the video on demand applications. In video on demand, we pre-code video into multiple rates. And in this type of application, viewers typically accept relatively long playout delay. As you all know, for video on demand, the popular protocols are Dash or HLS. With such a system, the server divides video into short segments and pre-code each segment into multiple read versions. And typically, the client prefetches up to, for example, 40 seconds of video before starting to play. Then the client requests successive future segments based on the estimated network throughput and target buffer length. It's important to know that prefetching absorbs the bandwidth variation and reduces the chance for freezing. So can we do that for 360 video? Remember, in 360, FOV prediction horizon equals to the end-to-end delay. With a long prefetching, we will have a long FOV prediction horizon, which will lead to low prediction accuracy. So a key challenge here is how do we enable accurate FOV prediction and yet prevent freezing? So we have proposed a two-tier streaming system as illustrated here. The bottom shows the base tier. The base tier includes segments that's coded in entire 360 scope in low quality. And the top is the enhancement tier. The enhancement tier includes viewports that covers different directions, and they are coded in high quality at different bit rates. Importantly, the client will use two separate buffers for the base tier and enhancement tier segments. It will use a long buffer for the base tier to prevent freezing, and it will use short buffer for the enhancement tier to reduce the FOV prediction horizon. So within this system, I would like to discuss two important questions in terms of streaming strategies. The first is at each request time, should the client download a BT segment or ET segment? in our design, we prioritize the base tier downloading, and we download the enhancement tier segments only when there's a sufficient, when the BT buffer size is sufficiently long. This way, a low quality 360 scope is always available and can be used if the downloaded ET segment does not cover the actual entire FOV, or if the ET segment arrives late, or if it's not requested. Thus, the base tier provides robustness to both network dynamics and FOV prediction error. So another important question is, how do we set the ET buffer length? Recall that shorter buffer would enable more accurate FOV prediction. On the other hand, longer buffer will reduce the chance for late arrival. So we have to select the buffer size appropriately to optimize the trade-off between these two. Our system further adapts the ET buffer size based on the FOV dynamics and network dynamics. For example, if the FOV is stable, we can use a shorter buffer. On the other hand, we can use, otherwise we will use, I'm sorry, we can use short buffer if the FOV is actually very dynamic, hard to predict. Otherwise, we can use long buffer to enable the network the buffer to absorb the network variation. So we have simulated our system using real-world wireless network traces and user FOV traces, and compared the two-tier system with two benchmark systems. The first benchmark system simply sent the entire 360 video for the robustness. The second system sent only the predicted FOV. We will look at the three performance metrics. The render quality refers to the quality in the pixels that's actually rendered. The freezing ratio is the percentage of frames that arrives late and is freezing. And the black ratio refers to the percentage of pixels that's outside the predicted FOV, but is actually in the user's FOV. As we can see, compared to the naive 360 system, the two-tier system can achieve much higher quality, and yet is as robust as the naive 360 system with a very low freezing ratio and black ratio. Compared to the single-tier system, we achieve about the same rendering quality. However, the single-tier system is very susceptible to both the freezing and black ratio. I forgot to mention the two-tier system has various several variations depending on how do we adapt the system with the FOV dynamics and the network dynamics. So now let me switch gear and to talk about our work in live video streaming. In live streaming, many people watch the same live event with slight time shifts. In these applications, shorter delay is preferred so that all the people can follow the same live event synchronously. For 2D live streaming, we can use similar ideas as for on-demand streaming, but with shorter prefetching buffer or shorter segments to reduce the delay, or we can use chunked transport to reduce the delay. For 360 video, we can now simply use the proposed two-tier system because the two-tier system requires a long prefetching buffer, and this would not be acceptable due to the low latency requirement. So we developed a flocking-based 360 video live video streaming system, and we leverage the fact that in the live streaming event, all the viewers of the same live event have slight time shift, thus forming a streaming flock as illustrated on the right. Some viewers are earlier, where others are in the back of the flock. Because of this, we could use the actual FOVs of earlier viewers to predict those of later viewers. We call this collaborative FOV prediction. As an example, user 1 here is a late viewer, whereas user 2 and user 3 are earlier viewers. When user 1 needs to download this segment, user 2 and user 3 would have already finished watching this segment. Therefore, user 1 can use the knowledge of where user 2 and user 3's FOV are to help to predict her own FOV. So once the FOV is predicted, we can allocate the rate among different tiles of a future segment, depending on the likelihood that each of them will be viewed. With the flocking-based system, we further control the latency of users to minimize the freezing event. We draw our inspiration from how the birds fly. As shown here, the birds often fly in flocks. In the bird flock, strong birds who have a strong headwind fly in the front, whereas weaker birds fly in the rear. This way, all the birds can fly fast. In live streaming, we also need to decide who to put in the front and who to put in the rear. So we consider users who have high throughput and stable network as strong users. We assign short initial latency and buffer upper bound. Because they have a good network condition, they would not suffer from freezing. And yet with the short latency, they can enjoy accurate FOV prediction without the help of others. We consider users with poor and dynamic network as weak users, and we assign long initial latency and buffer upper bound for these users to minimize the chance for freezing. And these users can use the viewing history of strong users to improve their FOV prediction. So as illustrated here. And with this design, we can improve the quality of experience of all the users. We have evaluated the performance of the proposed flocking-based system. And here we compare different FOV prediction methods, namely self-prediction and collaborative prediction, as well as the gain from engineering the latency. As you can see here, by comparing these two FOV prediction methods, on average, collaborative prediction can achieve more accurate FOV prediction with a lower KL divergence between the actual and predicted tile attention map. Furthermore, by engineering the latency among the users, we can reduce the freezing dramatically, as illustrated here, while maintaining a similar effective rate, which is the rate within the FOV. So now let me move on to interactive 360 video streaming. With 360 video, remote participants can interact in an immersive environment and thus have a more productive interaction. And the challenge here is that extremely low latency is necessary to facilitate user interactions. Typically, we require less than 150 milliseconds one-way delay. And that means all of this process has to be completed within this delay allowance. In order to minimize the delay, the FOV adaptive coding and delivery has to be conducted at the frame level rather than segment level, as in the video on demand and live streaming applications. So in our system, we use this structure to code a video frame. Here, the green represent the actual FOV, the gray represent the predicted FOV. The dark gray is the tiles that fall in the predicted FOV, and the light gray are a border surrounding it. In our system, we assign high rates for tiles within the predicted FOV. We assign a lower rate for the border surrounding the predicted FOV. And for both regions, we use motion compensated temporal prediction to maximize the coding efficiency. We also code a region known as rotating intra-region using a lower rate and we will slide this region from row to row so that all the tiles will be refreshed after a certain period. Such periodic intra-refreshment will limit transmission error propagation as with in conventional 2D video streaming, but it will also guarantee acceptable quality upon FOV prediction errors as illustrated here. And it helps to maintain temporal prediction efficiency in future frames. For example, these regions are not coded, but may be used for temporal prediction in the future. And we assign 0 rates for the rest. And our system adapts both the rate and the size of different regions based on the FOV prediction error and network dynamics. With the frame level FOV adaptive coding, incorporating temporal predictive coding is actually very challenging. As illustrated here, suppose I'm coding this frame, and this is the region I would like to code. And as you can see, some part of this region is also in the predicted FOV of the previous frame. Therefore, I can predict this region from here with a frame distance of 1. On the other hand, this part of the region, their corresponding region in the previous frame does not fall in the predicted FOV, so they're not coded. In the actual coder and decoder, this will be copied from the frame before. So the effective temporal time lapse between the reference and the region to be coded is 2. Generally, the time lapse for temporal prediction is temporally and spatially varying because of the FOV dynamics. A longer time lapse will lead to lower prediction accuracy and hence increased rate for the same quality. We have evaluated the impact of such time lapse on the coding rate or coding. As shown here, the rate increase in a kind of exponentially inverse exponential decreasing decay relation with the time lapse. So the challenge is, how should we consider such rate increase in FOV adaptive coding? In the system, we perform rate adaptation to ensure very low latency. As shown here, we adjust the rate both at the segment level and the frame level. We predict average throughput in the next segment, and then we optimize the region size and the rate allocation for this segment based on the predicted FOV accuracy and frame delivery rate. We further adjust target rate for each frame based on the sending buffer status. This is an evaluation of the proposed system and comparison with some other benchmark system. As shown here, the proposed system can achieve significantly higher quality compared to benchmark systems, which only use intra-coding in the predicted FOV. All the systems use similar rate allocation, therefore they achieve about the same delay. In all the systems, we were able to achieve a delay less than 100 milliseconds. So now let me move on to the problem of FOV prediction. Here I show you some sample FOV traces. As you can see, the FOV really changes very dynamically even within 10 seconds, you can see that there are a lot of changes. That's very hard to predict. So how should we predict the FOV? Here I present several possible avenues. The most straightforward approach is to predict a viewer's FOV in a future time from the FOV history of the viewer. In some applications, the server can look into the active video content and derive a saliency map from the content, and the user can use such saliency map to predict the FOV. And there are some applications where other viewers may have watched the same video or frames of the video, and then the user can use the history of other viewers, can use where other viewers have watched together with the viewer's own FOV history for the prediction. We have seen this when I talk about collaborative FOV prediction in our proposed flocking system, where the future video segments may have been watched by earlier viewers in live streaming. Now, for video on demand applications, the same video often have been watched by many other viewers in the past. And if the server restores such information, can use this information to help the current viewer to predict their future FOV. And we have investigated how do we use develop machine learning models for each of this approach. So in our work, we represent the FOV trajectory using the tile attention map or heat map. So essentially, we rely on the ERP representation, and each tile in the ERP has a likelihood of being watched. And based on the past FOV, we can generate this attention map sequence, and based on which we can predict how this map will look in future frames or future segments. So let's first talk about the very first approach, where we use only users' FOV history for the prediction. Towards this, we develop a sequence-to-sequence model using LSTM. So the encoder essentially model how the FOV attention maps evolved in time, and using that, the final hidden states is used to initialize the decoder model, which then continuously predict the attention map in the next time instant. Because the input is attention maps, we apply multi-layer convolutional LSTM, both for the encoder and decoder. This slide shows that people tend to focus on a few common salient regions when they watch a video. Therefore, we could use other users' FOV trajectory to help to predict a target user's future FOV. So in our machine learning model, we augment this sequence-to-sequence model by another LSTM model that models how other users' FOV evolve in time. And then we extract, we concatenate the hidden features from this other user's LSTM with the hidden features of the target user's LSTM. And then we combine them, and these features go through a fully connected network, a fully convolutional network, to generate the predicted attention map. Finally, in order to use the video content information, we assume that a separate saliency detection model can extract a saliency map from each video frame or video segment. And the saliency map will go through another FCN to generate features. And these features will be combined with the hidden state features, and from which to further predict the future FOV. And this plot shows the performance of the various approach. On the bottom is the result from using the target user's history. And there are various approaches here, but they have fairly similar approach. These are obtained using either other users' FOV or the video saliency or both, in addition to users' history. As we can see, with this approach, we can significantly improve FOV prediction accuracy when the prediction horizon is long, say, for example, over 5 seconds. So now let me summarize what I have talked about. As we can see, different applications have different constraints, but they also bring different opportunities. For on-demand streaming, because users tolerate a long delay, we can use a base tier that covers the entire 360 scope and use a long prefetching buffer to provide robustness to both bandwidth variation and FOV prediction error. For live streaming, we can use earlier viewers to help FOV prediction of later viewers. Furthermore, we can assign the latency among users to improve the quality of the experience of all the viewers. For interactive streaming, in order to reduce the end-to-end delay, we have to conduct FOV adaptive coding at the frame level. This brings new challenges for temporal predictive coding. In all of this, it's critical to consider robustness to both FOV prediction errors and network dynamics. We have also shown that deep learning is promising for FOV prediction. Using other users' FOV information and video content information is beneficial, especially when the prediction horizon is long. So looking ahead, given the fast development of 360 video capture and the display technology, I believe 360 video may become the way we video in the near future, whether it's to watch a movie, follow a live event, or conducting a business meeting. And video resolution is likely to continue to increase, making smooth streaming in dynamic networks more challenging. This prospect, however, brings rich and interesting problems for researchers in video coding, networking, and machine learning. We will need to continuously improve FOV prediction, FOV adaptive coding, FOV adaptive streaming, etc. More importantly, we need to conduct cross-layer design and consider multiple objectives in our design, including the rendering quality, playback smoothness, streaming latency, etc. It's important to follow a robust first principle in the system design to minimize the impact of FOV prediction errors and bandwidth estimation errors. It's also important to have a built-in adaptivity so that the system is responsive to the change in the FOV and network dynamics. So with all of our efforts and others, hopefully we can enjoy the ultimate 360 video someday in the future, in the not so distant future. Last but not the least, I would like to thank all my collaborators, including my colleague at NYU, Professor Yong Liu, with whom we have done all this projects together, who really is the main driver behind many of the ideas here. And the former PhD students, Dr. Fanyi Duanmu and Chengge Li, and current PhD student, Yixiang Mao and Liyang Sun. Liyang actually will be presenting the flocking-based live streaming system work later in this conference. I also would like to thank the support of our project by National Science Foundation, Huawei, and NYU Wireless Center. Here is a list of related publications. You can find the details about some of the work I talked about in these publications. With that, I'd like to thank you all for listening, and I'll be more than happy to answer any questions.
Thank you so much, Professor Wang. Thank you for sharing all this insight, both on the challenges and the possible solutions that we face with 360-degree video.
Thank you.
It was very interesting. And I see that the audience also find it very interesting because we have quite a few questions. And with this poll, we have an upvoting system. So we'll simply start with the highest voted questions and see how many we get through before the 15 minutes are up. All right, so the first question is, do you only use behavior for prediction, or do you consider other aspects such as video content?
Oh, yes, as I mentioned, we do, in some of the approach, right? We discussed one approach where we use the video content to derive a saliency map. And then we use the saliency map features together with the features derived from the FOV history. Yeah.
Indeed. So I guess we keep going to a related one. What is the most important metric in designing a 360-degree video streaming setup? Is it latency, quality of video, freezing? Are there any other metrics that you would like to highlight?
Well, so in addition to the latency, of course, you have to consider the quality, right? We want to, under the same network condition, we would like to maximize the rendering quality. So here the difference is that we only care where you watch, right? So not like in 2D video, you have to consider the entire video that you're coding. Here, you need to maximize where the quality where you actually defaults in users FOV. So our design is all kind of, I didn't go into the detail, but in each system, we try to maximize the average or expected quality given the kind of network constraint. So that average quality depends on FOV prediction accuracy as well, because because generally the FOV prediction is not 100% accurate. So some part of the FOV that you watch is from what you actually code, some part or the quality you code, some part will be maybe in the low, you coded with lower rate or was not coded. So we have to consider all of this. And we, of course, also have to minimize freezing. So like if you go into some of the actual papers, we have this kind of, we formulate this expected quality, which consider all of this. And in terms of quality, not only the kind of quality in the frame that you actually watch, but also how smooth your play is, right? Or like because of all this read adaptation, you may incur more discontinuity in terms of both within the same frame and across frame. So we also consider this spatial and temporal continuity.
That's good to hear. And now you can also see the questions posted live, I think.
Yes.
Good, thank you. So the next question is, what is the most, were you able to come up with a good, so we're speaking of quality metrics, and are you satisfied with the quality metric you use, or do you see potential improvements?
So in fact, I haven't got a chance to talk about this. No, I'm not, right? So we were just using essentially objective quality metric. And really, I think a lot of work has to be done in subjective quality for 360 video streaming that considers in particular the artifacts caused by kind of prediction, FOV prediction error, right? So in that case, you may have part of the render region was coded as high quality, part of it is low quality or frozen. And I think those kind of artifacts can be very disturbing. And to really evaluate that, you have to put it in a real streaming environment and see how does it change in time, how user react. So I think quality assessment of 360 video streaming in a streaming session is an extremely challenging problem and very important.
Yes. So the next question is on the field of view. Let's see, I'm not controlling the scrolling here. So are the upper tier field of views overlaid on top of the base tier? And does this require frame accurate synchronization in the rendering of the tiers when they are merged at the user side?
Very good question. So I can see somebody is really listening. So in fact, I didn't speak the details there. With our two-tier system, the video can be coded either in layered fashion or non-layered fashion. In our system, in our design, we actually compared the layer coding and non-layer coding. We actually found out, given all the constraints and also the layer coding, efficiency loss compared to non-layer coding, overall, it was better to use non-layer coding, meaning our enhancement tier segments are coded without reference to the base tier. So when you have the enhancement tier covering the area that you look, you would just use the decoded portion from the enhancement tier. In terms of synchronization, so basically we have like two separate buffers, right? For each segment, we always have the low quality rendering in all 360, right? For some segments, we have the high quality from the enhancement tier. So if we have the high quality, we just play that. And if not, we go back to the base tier.
Okay, so the next question we covered, and then we have the following one. How did you predict the throughput and the field of view in low latency environments?
That's another question I didn't address. Yeah, so because in the low latency case, you only need to predict a little bit ahead, right? In our case, the overall delay is only like on average 3 frames. So we use a very simple prediction approach. For the bandwidth, we use a what we call recursive least square approach, and which essentially use some kind of weighted average of the past throughput to predict the future. For the FOV, we use a technique known as truncated linear. So essentially, we assume the FOV within a short distance, if you look at that trajectory, is fairly linear. But when they have sudden change, you don't want to use the portion. So for example, if the past FOV goes like this, I don't know, can you see me or not? Not, right?
It depends on the audience. I can see you.
Right. So we assume that the FOV trajectory is linear, but if your past segment is not entirely linear, we only use the portion that's linear, and then we just assume that the future is following that linear path. So that's called a truncated linear prediction, and we found that. With such approach, the prediction, in fact, is very, very accurate. We achieve FOV prediction accuracy of over 98%, I think, thanks to the low delay or low latency in our system design.
So we have
and let me just say, for video on demand live streaming, the problem is a lot more challenging because you have to predict the FOV, a few seconds ahead. So for those, I think the technique I talk about, a deep learning based approach, will be very beneficial.
So I'll say that we do 2 more questions. So you have time now, audience, to upvote whichever question you want to answer. So the next question is moving on to a different modality. Is there much work on the influence on the audio modality, including spatial, on prediction of user behavior for 360-degree video? Do you know?
Oh, that's a very interesting idea.
Mm-hmm.
I personally am not aware of, but in fact, we did actually thought about it, when we start looking, but we haven't followed up. But I think that'll be a very interesting idea, especially when you have 3D sound in the 360 video, right? So it's likely you hear explosion, you would want to turn your head towards where the sound comes from.
Okay. Right. The next question is on your flocking-based system. Would it be so safe to say that it's effective only if users have the same field of view, or could you have it, or will this be for the whole panorama only?
No, we don't require all the users have the same FOV. So in collaborative prediction, what we do is we make use of the FOV of other earlier viewers, but we still use the history of the target viewer. So we kind of use both to predict. And also all the other users may not have the same FOV, right? So we have to kind of figure out a way how to combine or think of an average of others' FOV for that segment, but also how your own kind of trajectory has been. So I didn't go into detail, but so essentially we kind of use weighted average of both. We predict your future FOV from your past, but then we don't just rely on that. We also look at what others have seen in this segment. We use a sort of weighted average among this. But I think moving forward, using the deep learning approach that I discussed will be more promising.
Great, thank you. We do have 3 final questions, and I don't know if you have time, but let's see how far we get. So there's a question on tiles and the loss of compression efficiency and whether that's a challenge. So the final part is...
okay.
Yeah.
Sometimes I don't know which square you look. Yes, so we in fact investigated what should be the tile size considering the loss of efficiency in tile-based coding. So here actually, it's a tricky question. First of all, if you look, if it's a 8K 360 video, the whole frame is huge. We look at tile size of say 128, 256, 512, etc. And although using smaller tiles will reduce the coding efficiency, using larger tiles tend to waste more bandwidth because when you try to cover a FOV, if you use a larger tile, right, you tend to have those tile that's on the border. Many pixels in those tiles may not be actually be useful. So we did an experiment where we evaluated like the essential like a rendering quality with different tile size, found some intermediate size to be optimal. For example, with the 8K video, a tile size of 256 by 256 pixels seemed to be a good choice.
Great. That is all we have time for, and I will ask you kindly to share the remainder of the answers with us, or just write them into Slido. We can figure something out. That would be highly appreciated.
Yes, sure.
And
thank you very much. Yeah, thank you all the audience for the questions.
And I'll encourage everyone to keep the discussion going.